In the planning and configuration phase, you analyze your process sequence and develop a structured representation of your automation task. In the implementation phase, these determined structures are realized as program code elements for the target hardware of the controller. Realizing the automation task into a structured controller program is significantly facilitated by many properties of the Simatic software, as well as the firmware of the Simatic controller. In the later project phases, everybody involved also benefits considerably from the clear and stable program structures. We will now show you the properties which support the Simatic controller and the software. As a central component of an automation system, the Simatic controller first of all controls production machines, production plants, or plant engineering processes. Apart from the individual user program, the central control processor also processes the operating system, which is an integral part of the CPU, controls all processes on the CPU, configures its modules, and transmits all user data. From a user perspective, the CPU operating system is divided into three main components: the execution system, the memory model, and the system functions. The operating system controls the processing of the user program by means of the execution system. The interface between operating system and user program is provided by so-called organization blocks, OBs for short. The organization blocks are called and processed cyclically and continuously, or on the basis of the occurrence of defined events. This program division into various types of calls is referred to as task execution levels. The organization blocks contain the user program in form of subprograms called blocks. The user memory model of the CPU consists of various program and data areas, which are managed and organized by the operating system. The user program works with these memory areas. Via an extensive set of system functions already integrated in the operating system, each user program can extend its functionality or affect the operating system directly. The Simatic block architecture enables you to easily organize and structure the user program. In the following sections, we will discuss the execution system, memory, as well as block architecture in greater detail. As already mentioned in the overview, via the interface of the organization blocks, the operating system of the CPU offers you various so-called execution levels. This enables a precise division of the user program into largely independent program parts. The execution system provides the correct call sequence of the user program parts. Generally, you have the option of splitting your user program into the following sections: cyclic continuous processing, startup, interrupt, and error behavior. After switching on the power supply or pressing the mode selector at the central controller module, the operating system calls the reserved organization block for the startup. This enables you to specify a clearly defined start behavior for your plant. One example is to have all drives move to a basic position upon recurring of the mains voltage before starting with a new production cycle. After ending the startup organization block, the CPU starts processing the actual main program which controls the plant. This program is contained in organization block OB1. It is called by the operating system and processed step by step. After the CPU has terminated processing the program, it is immediately called up again. A new cycle starts. This means the main program in OB1 is continuously and cyclically processed. This cyclic program processing is typical for programmable logic controllers, and with a short cycle time, it causes a virtually parallel processing of all instructions. The length of the program to be processed in OB1 determines the minimum cycle time, hence the reaction time of the system. Sometimes a process requires reacting immediately to a certain event, irrespective of the reaction time due to the free cycle. The CPU provides the execution level of the interrupts and calls the allocated organization block. The interrupt program now determines the reaction to this external or internal event. Interrupts can be initiated by the plant, this is referred to as a hardware interrupt, or be triggered by the CPU depending on the time. This includes the group of time-controlled interrupts. After terminating the interrupt program, the CPU continues processing the interrupted cyclic main program. When certain errors occur, the CPU calls the organization blocks of the error execution level. The error program you called from the organization block now determines the reaction to this event. The system basically distinguishes between synchronous and asynchronous errors. A synchronous error is always due to a location in the user program, such as a programming error or access error to a non-existent I/O module. An asynchronous error, on the other hand, is an error independent of program processing. If, for example, a broken wire has been detected in a temperature sensible suitable for it, the diagnostic system integrated into the operating system calls the organization block OB82. The user program in this OB can now react to the error situation. For example, send a message to the operator control and monitoring system or switch off an affected part of the plant. The cyclic OB1 always has the lowest priority class, which means that the main program can always be interrupted by external or internal interrupt or error events. If two events are detected simultaneously by the operating system, the event with the higher priority is always processed first. Each organization block in one of the execution levels has been allocated to a certain priority class, which controls this mutual interruptibility. This interruptibility also applies for interrupt and error OBs. All user program objects are located in various organized memory areas of the CPU. Different variable areas are the basis for the communication between the program parts and the system. We will now follow the course of a user program from the programming device through the various CPU areas of the user memory model. The user program and the parameters of the Simatic automation system were generated offline on a programming device using the Simatic Step 7 software. In the operating mode stop, a download of the user program and the configuration parameters of the hardware into the load memory of the CPU is triggered. The load memory is designed as memory integrated into the CPU or as plug-in memory card. When using flash EPROMs and micro-memory cards, the entire user program stored within is secured against power failure. After the download, the CPU operating system interprets the configuration data and on starting up sets the parameters for the modules which are part of this CPU. In the transition between operating mode stop and run, the program code required for processing the program as well as the user data are copied from the load memory into the work memory. The work memory has been designed as fast and entirely CPU-integrated RAM memory. In run mode, the execution system ensures processing of the user program. During the runtime, the user program operates with operands and variables located within the system and work memory. The system memory contains the following sections: the process image, which is the interface to inputs and outputs of the module. At the beginning of each program cycle, the operating system automatically ensures that the complete image of all parameterized inputs and outputs is updated and their status filed in the so-called process image. Access from your user program is then usually performed via this consistent I/O image. Memory bits are a universal variable area which can be used globally within the entire user program. Timers and counters are managed by the operating system. They can be used for easily realizing wait or monitoring times and part load counts without additional hardware and with very little programming. Temporary variables which during program processing lead to dynamic intermediate storage are filed in the local data stack. The block stack and the interrupt stack are used for internal management of the call hierarchy. For diagnostics purposes, they are only accessible in stop mode. Additionally, the system memory contains buffers for communication jobs to other stations and system message buffers for all of the diagnostics events of this station. The classification of memory areas and access methods by the user program is independent of the selected programming language or the CPU type. This uniformity is the basis for easily reusing programs and libraries also across different CPU types. A complete plant or production machine mostly consists of different technological parts, which can be separated from each other. For the technologist, a machine for labeling cups, for example, consists of the material feed, a labeling unit, and the packing unit. The automation designer can subdivide each technological unit into further independent subtasks, such as conveyor belts, lifting units, etc. If functional units can be identified, which can be used jointly by several technological units, this is referred to as a structured approach. In this example, this could, amongst many others, be a motor control, valve control, failure display, or part load count. This form of structuring is the basis for simple solutions to complex tasks. Step 7 supports you in this task with its programming and block concept. A Step 7 block is a part of the user program separated by function, structure and purpose, which enables structuring extensive and complex control tasks. As a user, you have the advantage of easier programming due to smaller functions, better overview over the entire plant, easier testing and commissioning of your plant as each component can be dealt with individually, and the possibility of reusing a once realized functionality by generating libraries. Let us take a closer look at an example taken from a possible realization of this plant structure. In principle, an entire program can be instruction by instruction contained in one single block, for example the organization block OB1. This is referred to as a linear program. This type of programming, however, has the disadvantage of not being clear, hence prone to errors, huge programming requirements, and increased memory requirements. The Step 7 block concept is predestined for the structured realization of this task. For processing the blocks, which control a technological or functional unit, they are called successively or stacked in an organization block. After they have been processed, the program automatically jumps back to the return address in the calling block. Step 7 offers you different block types for encapsulation of your subtasks depending on the application. As shown in the preceding section on the execution system, the organization blocks are the interface between the operating system and the user program. The main program is generally located in the cyclically called OB1. For example, OB1 calls the technological unit of the first conveyor belt. This subtask has been realized as function block FB for short. A function block can be parameterized flexibly and has its own memory in form of an instance data block. This data block, DB for short, is created by the program editor in an instance on first calling the FB and is primarily only available for this FB for data exchange. The result of calculation and logic operation of a function block can therefore be dependent on the status of the current call parameter and on the status of stored data from earlier cycles. In a function block, further blocks can be called. An example is the task of displaying and processing error signals with a reusable function. A function, or FC, is used for programming frequently recurring automation functions. It can be parameterized and can return an optional return value to the calling block. Functions generally do not store any internal information beyond their runtime. They only communicate via their input and output parameters. System functions, or SFCs, are parameterizable functions integrated in the operating system of the CPU, whose number and functionality are fixed. In this example, the current system time can be read from the operating system of the CPU via an SFC. Similar to the function blocks, there are also parameterizable system function blocks, or SFBs, integrated in the operating system, which on being called only need to be supplied with an instance data block. Structured and type-coded user data can be stored in data blocks. There are two ways of realizing the application of data blocks. As a global data block, which can be used as free data block by all other function-related blocks, and as instance data block, which is always assigned to a function block and only contains the local data of this block call. After the program of the first conveyor belt has been processed completely, all further plant parts intended for execution are successively called in OB1. Identical plant components, such as a further identical conveyor belt, can now be processed by simply calling the same block with other I/O parameters and a separate instance DB. This way of creating the user program illustrates how simply, clearly displayed, execution and memory optimized, reusable programs generated in the same or in different projects can be generated with blocks. A simple user program is used to illustrate how a function block communicates with the various memory areas of the CPU via its parameter interface. The ladder diagram displayed here implements a simple multi-usable motor block. The motor is switched on and off via push button. The on status is additionally displayed via a blinking signal. The block can be used repeatedly for the same motor type. A certain motor is selected merely by assigning the interface. The program of the block, its function, remains unchanged. The inputs are addressable via the memory area of the process image and are connected with the input parameters of our block. A program-wide uniform enable signal for all motors is located in a global data block and is also connected to the input parameter. The central blinking signal is automatically assigned to a global memory bit via parameterization by the CPU, and it is connected to a further input parameter. The controlled motor contactor and the blinking light are connected with the address in the process image of the outputs via the output parameters. The status of the storage element in the program must also be maintained after terminating the motor block. A static variable is therefore created in the declaration section of the FB. For an FB, all parameters, temporary and static variables, are stored in the instance data block. The operands of the user program used in the block are exclusively switched via the symbolic name of the block parameter and static variables of the declaration section of this block. The functionality is now completely encapsulated. Physically, the block exists only once in the memory of the CPU. However, it can be called up in the program many times using an instance DB.